This video is the first in a series that will hopefully provide a little bit more context as to why and how you use PyTorch for certain deep learning tasks, while at the same time being a lot more concise than something like the full Fast AI course that's really geared towards a kind of semester-long timeline. So what is PyTorch exactly? Well, it's, not to state the obvious, a deep learning library, but that begs the question, what is a deep learning library? And I like to think of a deep learning library or a well-designed deep learning library simply as neural network pseudocode. It's a way to kind of best represent the concepts and the operations you need to do mathematically with deep learning and neural networks, and is a way to represent or express those in code to efficiently run computations on actual hardware. And PyTorch does this through a nice NumPy-like interface to GPUs. It started off as a interface to NVIDIA GPUs and the CUDA library. It has since broadened to many more devices, but at its core, PyTorch lets you run linear algebra operations on a GPU, and it also provides what's called automatic differentiation. This is a way to compute gradients of somewhat arbitrary functions defined in your code. And this is really what powers the learning in a neural network, or the optimization, the training, the learning of the weights that you need for your network to actually give good and accurate predictions. So PyTorch has a variety of ways to create tensors, just like NumPy has a variety of ways to create arrays. And the most straightforward, possibly, is just the tensor constructor, where you call torch.tensor and pass in this case, just a normal Python list. And we can see here what gets returned is a PyTorch tensor. But notice that while we passed in a list of integers, internally, PyTorch converted these into floats. And if we do want to actually convert a given tensor, let's say this is x, to a different data type, x to start with has d type or data type float 32. But if we want to cast it as, say, an int, we call .int. And if we want to cast it as a double, we call the double method. But maybe much more useful than just initializing torch.tensor with a Python list is to use one of the, call it, constructors, where we can create a range, in this case, x from 0 to 9. Additionally, we can do something like zeros, and this does the same with zeros, or even ones. And this does the same with ones, and so forth. There's a variety of these constructor functions. I'll leave a link to the documentation in the description, but usually it's a question of figuring out which is most similar to the type of data you either need to generate. But in practice, you often are reading a data set from a different source, like a data set of images or text or so forth. So a lot of these constructors are useful for just kind of prototyping and examples of stuff. And just like in NumPy, we can get the shape of a tensor. In this case, it's a vector. It has 10 elements. But if we do want to make it into a more interesting shape, we can call reshape. And as long as the number of elements of what you're reshaping it into matches what you start with, in this case, 10 elements, everything should work fine. So we can reshape 10 elements into a 2 by 5 tensor. Here we look at the shape and we can see 2 by 5. But if we want to, let's say, make it into a 3 by 5 tensor, we don't have enough elements. We're going to need 15, but we're only starting with an A range of 10. So that's something to keep in mind when you're debugging, is that matching shapes with tensors goes a very long way to figuring out where your issue is. So I often when I'm debugging, use .shape a bunch, and or look at the tensor output itself just in a terminal or on the console like so. And with tensors, you often hear this term thrown around, the rank. And the rank is similar to dimension, like 2-dimensional, 3-dimensional. It's maybe more specific in that dimension often gets used in a variety of different ways in mathematical or machine learning or data science contexts. And the shorthand is to actually look at the length of the shape. In this case, if we look at the shape of our A range, it's a size or torch.size object with a length of 1. And this makes sense because if the size is length 1, it really means we're dealing with a vector, and a vector is a rank 1 tensor. Now, if we reshape this like we had before to 2 and 5, we look at the shape. Now we have a length of 2. So instead of a vector, we now have a matrix because we have a length of 2 for our torch.size. And if we reassign that to x and look at the rank of x, we now have a rank 2 tensor. And you can basically have an arbitrarily high rank for your tensor. You can have a rank 1000 tensor, even though in practice, your rank is often reflective of your data type. So if you're dealing with image data, you might have rank 3, since a color image has rows, columns, and then multiple color channels, red, green, and blue. And the last thing I wanted to talk about in kind of how PyTorch tensors are the same, but also different than NumPy, kind of some gotchas, is that if you try to pass in a PyTorch tensor to another scientific Python library, often the conversion to something like NumPy works fine, but I often like to explicitly convert our torch tensor with the .numpy method into a NumPy array explicitly, just so I can make sure that no weird type conversions or other stuff's happening. If I'm, say, visualizing a tensor with something like matplotlib that really expects NumPy arrays as input. And all of this is good and well. Hopefully this API for tensors, for kind of these operations, feels very familiar if you're coming from scientific Python, if you're coming from NumPy, but PyTorch wouldn't be that useful if all it was a NumPy clone. So now to the second pillar of kind of PyTorch, the magic. The first pillar, I would say, is this NumPy-like API for working with tensors. And the second part of kind of PyTorch's uniqueness is working with GPUs. And to check to see if PyTorch can actually find your GPU, if you do have a GPU, you have torch.cuda that is available, which is going to return true both if you have an NVIDIA GPU, but also if you have an AMD GPU. PyTorch somewhat recently just got support for Apple Silicon, and this is namespaced under the MPS for Metal Performance Shaders. And if you are working on Mac OS, a new MacBook, say, with Apple Silicon, MPS that is available will be able to use the kind of GPUs. And when working with GPUs in PyTorch, maybe the biggest difference from something like NumPy is that now, since we have both CPU operations and GPU operations, all of our tensors can either live in the CPU, which is in the RAM, or on the GPU, which is in the GPU's memory. So if we want to figure out where a given tensor is, we call the device attribute on that. So here we have X, we initialized it. The default is to initialize on the CPU, and our device here is the CPU. Now, if we want to put this on the GPU and use it with GPU accelerated operations, we use x.toCUDA, which now we can see our device, instead of listed as just the CPU or just as the default, is listed as CUDA. And if we want to send it back, this isn't necessarily something you would do in practice. This is just an example. We can send X to the CUDA. And keep in mind, with most, if not all, PyTorch operations or methods, they often return a copy of the tensor they're being called on. So x.toCUDA is returning a copy of X. So here, if we look at device of X, we still have it on the CPU since that is what it was initialized on. And if we do want to kind of permanently put X on the GPU until we take it off, we have to basically overwrite the variable or save it into a new variable. So now if we save x.CUDA into the reference for X and we look at the device, now we maybe properly have X on the CUDA. And now if we're doing some operations or a lot of operations that we all want to happen on the GPU, we don't have to worry about calling .toCUDA every time before we call a method or a function. And while PyTorch makes it super easy to basically transfer data from your CPU and RAM to your GPU and the GPU memory, it does have kind of a few gotchas that you have to be aware of. And one of them is that you can't actually operate between the CPU and the GPU. In other words, if we want to do something like this, X plus another tensor that is the same dimensions, we're going to see this runtime error, which is maybe one of the more common, but thankfully easier to debug errors. It basically says all of the tensors need to be on the same device, whether that's both of them on the CPU or both of them on the GPU. So we can either put this new tensor on the GPU and it works fine, or kind of do the opposite and bring this X back from the GPU using the .cpu function. So .cpu is really an alias of .toCPU. And just like you can call x.toCPU, you can also do x.CUDA to put it on the GPU. So there's a lot of kind of flexibility in the library, and part of that's historical since it did evolve from the LuaTorch library, and some of it's trying to conform to Python, some of it's trying to conform to the API of LuaTorch, some of it's just trying to match kind of how the internal kind of core library that might be using C++ is built. So whenever I am dealing with errors or debugging or new functions, usually I always make it a point to look at the most recent documentation, either for the API or tutorials for PyTorch, since things can change, especially between major versions. And I will put out this caveat that while it is easy enough to use for general purpose machine learning, you can, in theory, program a somewhat very efficient linear regression in PyTorch if you want to. But just due to kind of the setup, the infrastructure, sometimes the mismatch between the API and the algorithm you're trying to implement, it may not be as easy to implement in PyTorch as it is in something like just pure Python or something like using scikit-learn. So it's really, I say, only necessary, or rather, you know when it's necessary because the other stuff you've been trying is either too slow, you can't run it on enough data, or the algorithms themselves just aren't complex enough. As I refer to it, PyTorch, I really am talking about a whole ecosystem of libraries. And in this ecosystem, we have both a Python as well as a C++ API, which we'll talk a little bit more about. But PyTorch itself, you can think of it as this core library that does a lot of the heavy lifting for us. It has a neural network module in it, torch.nn, which is probably most of what people use, or at least most of what people interface with, since PyTorch is really built around this idea of building or programming neural networks. This provides things like neural network layers, activation functions, and tangentially kind of optimization procedures. And the second bit of the core is this automatic differentiation library. In PyTorch, it's referred to as AutoGrad. And this is kind of where the magic of PyTorch happens, but it's often underneath the other higher level bits of the API. So you usually don't interface directly with this unless you're doing or researching some specific optimization procedure itself. And the secret sauce of PyTorch is that it exists as kind of this in-between layer of Python code you write which executes on PyTorch core. And PyTorch core basically calls out to any number of what it refers to as backends. And this is really just the computation or the hardware aspect of where your code is actually executing. This could be the CPU, it could be an NVIDIA GPU and use the CUDA library, it could be Apple Silicon, or it could be something even as exotic as a TPU, which is Google's tensor processing unit. So the beauty of it is if you write code in Python, you can execute that same code with very minimal changes on the CPU to test out your algorithm before maybe scaling it up to run on GPUs or even run in a distributed fashion on multiple GPUs. And in addition to kind of the core PyTorch ecosystem, one of the reasons that I use PyTorch, to be honest, is the third-party kind of libraries or ecosystem built on top of PyTorch core, much like a lot of scientific Python libraries are built on top of NumPy. Now, the libraries I use the most, because there isn't really an alternative or an analog, are the Hugging Face diffusers and the Hugging Face transformers library, which, as their names state, provide diffusion models in diffusers and transformer models in transformers. But both of these are so broadly applicable, it covers most, if not all, use cases that I've encountered. And besides those two in the Hugging Face ecosystem, which are personally my favorites, there's other interesting libraries like the FastAI library, which is kind of paired with the course in the book, which makes it a lot easier to just get started and up and running with deep learning. There's the PyTorch Lightning, call it meta framework. It's a framework to help you train and deal with a lot of the boilerplate around just infrastructure around setting up these neural networks. And with this kind of overview to call it deep learning libraries in general, you might be wondering, well, where does PyTorch fit in? I've heard of TensorFlow, I've heard of Keras, there's a new library, new-ish comparatively, called JAX, and all three of these actually, TensorFlow, Keras, and JAX, are all Google projects, and they all really focus on or excel at one aspect of what I like to call here the deep learning software trilemma. And the thing with trilemma is kind of try to visualize it in this triangle diagram here, is that you often have these opposing forces of how good and efficient is the library at productionizing already trained models. Let's say I want to do inference on a mobile device or an embedded device, or I want to do distributed inference, or I want to kind of deploy it to any number of hardware or architectures. How easy is it to actually program, and how, maybe more so than how easy is it, how efficient can I be as a developer or an engineer? And the last bit I label here as research. It's more the things the library does that make research easier. These are things like how flexible is it, how adaptable is it to different situations and setups in terms of maybe I'm doing some research on a non-traditional deep learning architecture and it doesn't fit into the normal standard paradigm that a lot of the kind of conventional deep learning has evolved into. So with each of these Google projects, they kind of specialize or they came out of one of these points of the triangle where Keras really kind of came into its own by making it way, way easier to deal with all this stuff than TensorFlow core itself. TensorFlow is still probably one of the best for putting machine learning models into production. And JAX, I say relative newcomer, it's a few years old, but it really emerged out of this need to research more kind of cutting edge architectures, patterns for training these things at incredible scale, and was really built around Google's XLA, or the framework that lets you run these operations on tensor processing units. So it's both good for kind of its flexibility, but also its efficiency in just utilizing hardware when training. And I like to think of PyTorch as kind of this Goldilocks that sits in the middle. It's often like Python, it's not the best at any one thing, but it's the second best at everything. And this is kind of the jack of all trades, master of none type of deal where it's good enough and often more than good enough for each of these points of the triangle. And the reason why I keep coming back to PyTorch is it does all of these well enough and it doesn't need me to switch between frameworks or context switch between APIs or deal with a lot of back and forth between different libraries, since most of what I do kind of touches a little bit on all three of these.